the first thing, the only thing that connects it with the first lecture, where I described the geometric approach to quantum theory, is that the starting point is the set of states. The set of states is represented in a very concrete way by functionals that I call L functionals. And let me start with the construction of these functionals, starting with algebraic approach. So sorry, something wrong. Let me start with quantum theories that are obtained by quantization of series represented in classical way by means of Lagrangian or Hamiltonians. And then there is a standard way to quantize this series. So really, you have a phase space. In the phase space you have coordinates, generalized momenta denoted by pk, and generalized coordinates denoted by qk. And you quantize this physical quantities, you will get operators that satisfy the standard canonical commutation relations, which is they are reproduced on this slide. It will be more convenient for me, but not quite necessary, to introduce other quantities denoted by A star and A that are linear combinations of P and Q. And of course you can go back and forth with these coordinates. So that's really, this choice doesn't really mean anything. So, and after that, so you quantize these guys, and you have operators. These operators satisfy some this commutation relations. So you have representation of commutation, of canonical commutation relations. In mathematical language, this representation of algebra is called Weil algebra. And but the problem is that when you are dealing with quantum mechanics, then you have finite number of these operators, finite number of degrees of freedom. And then there exists one and only one irreducible representation of canonical commutation relations.
You written pre-Hilbert space. Why it's not just pre-Hilbert space? What is pre-Hilbert space? What is the difference with?
So I didn't pronounce this word yet. Let me explain in a moment. Then what you would like to do in the case of infinite number of degrees of freedom, you have precisely the same picture, but many representations of canonical commutation relations, and you should really consider all of them. So that's, this is a problem, because you do not know what is the representation to choose. One of this representation is a standard one. This is called Fock representation of canonical commutation relations. It contains some cyclic vector that is annihilated by operators AK. And physicists usually work with this representation, Fock representation. Let me say, explain some words that are written here on this slide. So what I did I say? I considered operators AK and A star K that in physics are called annihilation operators and creation operators. But really what is convenient is consider all linear combinations of them. Not all linear combinations, but at least some linear combinations. K in my transparency, in my slide, was simply an integer number. But it is not quite convenient in all cases. Sometimes it is convenient to consider K as a real number or an element of some Euclidean space, or maybe this can be a pair of continuous parameter and discrete parameter. So to have these cases presented together, I can consider linear combinations of this operator AK and A star K with some coefficients. And if K is continuous parameter, then A of K is really a generalized operator function. The operator sense can be given only to integral of A of K multiplied by F of K. So I consider therefore operators depending on some functions, a function f. And if I would like to have the possibility to write down commutation relations, I should have inner product of these functions f. So therefore, the picture that I have is as follows. I have operators AF and A star G that satisfies commutation relations written here. So you have two operators A commute, two operators A star commute, and commutator at AF and A star F is a number that is linear with respect to F and J, so it can be considered as inner product in some space. And I do not require this inner product gives a structure Hilbert space on F, on this elements F. I require only the existence of inner product with standard properties, and this means that I am dealing not with Hilbert space but with pre-Hilbert space, which means that I have assume all the axioms except the axiom that Hilbert space should be complete.
Do you require the completion of the Hilbert space?
You can go to completion, but the separators, if I would like to have, the separators defined everywhere, then I should not go to the completion. I should live in some pre-Hilbert space again, where you do not have completeness. But this is really a question about definitions. You always can go to the completion, and this is absolutely okay. The standards, these problems that operators are not well defined everywhere. This problem is not very serious. Mathematicians know how to deal with this problem. So, but in any case, what is important that there are many representations of these commutation relations. It is easy to construct a lot of representations, but instead of doing this, I will explain that there is no necessity to consider all of these representations if you are working not with vectors in Hilbert space, but with states. So, what I am doing, so I consider all of these representations. The simplest of them is the Fock representation, and I suggest the following construction. Look, what I am doing. I am defining an operator called W with index F. This is a product of exponents of operators A star and operator A, depending on some arguments F and F bar. And I say that vectors in Hilbert, that states in Hilbert spaces can be represented by density matrices everyone is living in its space. But I consider this formula, the trace of operator W multiplied by density matrix K. And what I am saying, that this is a function which is well defined for every density matrix and every function f from my pre-Hilbert space. Let me explain why.
What is K?
Sorry?
What is K? K.
K is any density matrix. Any. Density matrix is by definition of quantum mechanics, is a self-adjoint operator which is positively definite and has a unit trace, which means in particular that it belongs to what is called trace class. Trace class consists of operators having well-defined trace. So I don't want to give precise definition of trace class, but it is sufficient for me that if you multiply operator from trace class by any operator which is bounded, then you get again an operator from trace class. It also has a trace. And let me look why these considerations really give a statement, a very simple one, that these operators, these functions Lk, are well defined.
That's all. I'm confused. This K is an operator where?
Sorry?
In what space? Is it your pre-Hilbert space?
So
it's complete.
this F belongs to this pre. So remember that these operators A of F are defined if F belongs to some pre-Hilbert space that I believe was denoted by E. So this L is a well-defined function on this pre-Hilbert space.
So you consider then K as an operator on the pre-Hilbert space? This K, whatever you call the density matrix, is it an operator on the pre-Hilbert space? Then you cannot speak about the trace class. Or it's an operator on its completion, then you...
Sorry, I think that I would prefer to do that.
You multiply WF, whatever, with head by K, so...
Yeah, please wait with your question for 1 minute, okay? So, look then, I did not stress this in the definition, but operators A star and A, they should be really Hermitian conjugate operators. So that remember that P, they were defined in terms of P and Q that really are assumed to be self-adjoint operators. And you can, and when you go to A star and A, you get Hermitian conjugate operators. But these operators are really unbounded, and therefore the operation, this statement that their Hermitian conjugate is not mathematically is not very well defined. But right definition of this is that the operator minus a star of f plus a of f bar is self-adjoint. The notion of self-adjoint operator is very well defined. In any case, this is even in this if the operator is unbounded. So therefore, if you have the self-adjoint operator, then you have again a well-defined e to the exponent of not of self-adjoint operator, but of self-adjoint operator multiplied by imaginary unit. So you have this exponent of operator of the form I multiplied by self-adjoint operator is a unitary operator. So this operator that is written here, e to this something, is unitary, and therefore it is this operator is really bounded operator. Here you have an exponent of unitary operator in the definition of the functional, of L functional. You have a product of two exponents. But it is very easy to check that this product of exponent, the exponent of the sum, they coincide up to finite numerical factor. This means that operator WF is a bounded operator, and the formula for the functional L is really well defined for every density matrix in every representation of canonical commutation relations. This is the time to ask your question. So?
You already answered it.
Yeah, this was my suspicion, that you simply should wait 1 minute and the question will disappear. Okay. This is the first thing that I wanted to say. It is absolutely trivial, but it's important. So what? So there are questions about this. What are the functions that I can get this way? And the answer is, first of all, that this functional is not really analytically, doesn't depend analytically on the function f, and therefore I will change the notation. I will write L of F bar and F. That's usually in physics, when you consider non-analytic function, you use these notations because later I would like to consider derivatives with respect to F bar and F separately. It satisfies some normalization condition if you have F equal to 0, then the operator W is simply the unit operator, and you have trace of K, which is equal to 1 by definition. And K is a positive definite matrix. The density matrices in quantum mechanics are positive definite. So therefore you have some positivity condition that should be imposed on L. It is you can write them down, but instead of doing this, I will explain all the stuff, how all the stuff works in algebraic formulation of quantum theory. Look. What happens with the algebraic approach? What is the algebraic approach? So you are starting with unital associative algebra with involution, called star algebra. And then you can define the notion of state in this algebra. This is a linear functional on the algebra that satisfies some positivity condition. This positivity condition is that linear functional on x star multiplied by x should be non-negative. And so then you can define normalized states, imposing the condition that omega of 0 is equal to, omega of 1 is equal to 1. Or non-normalized states, then you define only positivity condition. And then you get really either a cone of non-normalized states denoted by C, or you get the set of normalized states denoted by curly N. So this can be applied to any algebra. What I am doing, really, I am applying this abstract notion of state to the case of Weil algebra. And I describe the states in a very explicit way as functionals on some space E. So the only problem is that, of course, I should take Weil algebra as the algebra that I am starting with. But the problem is that this is not a very good idea, because while algebra consists of unbounded operators, it's generated by unbounded operators A star and A. What I'm doing, really, I'm considering exponential form of while algebra. What is the exponential form of while algebra? This is simply you take these operators of the form WF, they are bounded. And they, let me take them, say in Fock representation, in Fock space. And you can consider the algebra generated by operators WF. So I would let me say that this algebra is really an algebra which is close with respect to operator norm. So we will have a good algebra, C star algebra. I do not need this the definition of C star algebra, but this is a good algebra consisting of bounded operators. It has some topology. So, and now, what can I do? I can consider linear functionals on this algebra. Remember, the states are particular cases of linear functionals on the algebra. And the first remark is that linear functional on this exponential form of Lie algebra can be represented as nonlinear functional of f. This f is, runs over pre-Hilbert space E. This is a nonlinear functional on space E. And this fact is obvious because really linear combinations of operators WF are dense in the exponential form of Weil algebra. So therefore, linear functional on exponential form of Weil algebra is defined, is specified by this nonlinear functional. This is a trivial remark, but it allows me to work, to give completely analytical description of quantum theory in the case of infinite number of degrees of freedom in the language that does not require consideration of this infinite number of non-equivalent representations. So these linear functionals are represented on Weil algebra are represented as nonlinear functionals on different space. And a part of this will be as a space denoted by L, curly L, and the space of nonlinear functionals that correspond to positive linear functionals are denoted by curly, this case by curly n, and this is the space of my L functionals. I will work with it. So, and the first remark is the following. That I can translate an action. So you have density matrices. They are they lie in different Hilbert spaces. In all of the spaces, you have operators A star k and ak. You can take the density matrix and multiply by ak or by a star k from the left or from the right. And the remark, also a trivial remark, is that all the separations on density matrices can be translated to very well-defined operators on L functionals. And this slide gives you the following picture. So you have these operators acting on L functionals that correspond to operators in different representations of commutation relations. So this is, I took operators ak and a star k. I can multiply these operators, take composition of them, then in the L function, so we have composition of corresponding operators. So basically, what I'm saying here, that everything, every operators on density matrices that is expressed in terms of A star and A, every operator of this kind can be translated to L functionals, everyone. So, this is for while algebra. But basically, in algebraic approach, you can start with any algebra. And again, you have more or less the same situation. And what I would like to say that if you have any element of this algebra, you can multiply density matrix from the left or from the right. Or you can avoid the language of density matrices. You can consider linear functionals. Then you have linear functional omega of x, and you can have a new functional taking omega of ax or omega of xa. So you have, in one case, it's better to write the adjoint operator, but this doesn't matter really. So basically, what do we have? You have operators of the type A, if you have operator A hat acting in the space of CCR, then you have two operators acting on linear functionals. One of them is denoted by A, the other denoted by A tilde. And again, you have a more or less trivial remark that if you have an equation of the form when on the right-hand side you have A plus A tilde, then this evolution according to this different differential equations has the property that positive functionals go against the positive functionals. And so basically these operators of the form A plus A tilde, they act on L functionals. So now you can really say that you can formulate any you can formulate everything in quantum mechanics in terms of L functionals. You can forget completely about representations of canonical commutation relations. So basically, what do you need? You have the states, and the only problem is that the set of states that I denoted by n doesn't have any simple description in the case of Weil algebra. But this more or less doesn't matter. You can prove that these Gaussian exponents, this negative of the form e to the quadratic form, which and you have here negatively defined quadratic form. This belongs to this state n. This gives you a lot of states, but after that, you know that basically you can get many other states. Take the Planck evolution operators that preserve this requirement that you have a state. So basically, what you are doing, you can take the Hamiltonian. I'm returning to usual quantum mechanics. You can take a Hamiltonian. You can represent the Hamiltonian in terms of operators P and Q, or in terms of operators A star and A. I represented it in terms of operator A star and A. But this is not really relevant. And this Hamiltonian is not well defined in Fock space, usually. For example, if you have translation invariants and you have at least one terms containing all only operators of creation, only operators A star, your operator is not defined in Fock space. So basically, if you work on standard formulation, then you can you can write down Heisenberg equation, and Heisenberg equation can be well defined in some situations. Maybe they are not defined, but anyway, you have a lot of problems with considering this Hamiltonian inappropriate representation of commutation relations. Okay, but now in the formalism of L-functionals, you usually do not have this problem. So really, you can write down the equations of motion for L-functionals. And these equations of motion for L-functionals are in many cases very well defined. In particular, what happens in standard statistical physics? In standard statistical physics, you have a well-defined theory in finite volume, usually. But if you would like to work in infinite volume, you will get finite volume. You can work in Fock space. However, in infinite volume, you cannot work in Fock space, and so that's your operator is not well defined. What you are doing is you should work in finite volume, make calculations there, and then define correlation function in infinite volume using the limit omega volume tends to infinity. In the case of L-functionals, in this case, you simply don't have any problems in infinite volume. Everything is fine. So, this is this is something that this general words that I wanted to say. So probably it would be helpful if I consider the simplest example. And the simplest example is the case of quadratic Hamiltonian, which is written here as integral of epsilon of k, a star k, a k, dk. And in this case, as I have said, everything is very nice in finite volume. And moreover, you can thank you. Moreover, you can make calculations in finite volume, and then look what happens in infinite volume. Let me look. So this functional, this Hamiltonian is commutes with momentum operator. So it is translationally invariant. And you can define these L functionals of the form of quadratic exponents that are written here. They are also translationally invariant states of, they are stationary with respect to corresponding Hamiltonian. So this is a good set of states. And moreover, you can consider what is called Gibbs states, this equilibrium state that can be represented in standard classical mechanics as exponent of beta minus beta multiplied by Hamiltonian. This is some simple calculation in finite volume allow to write down some equations for equilibrium state, and this is done on the next page. And this equation can be written in finite volume, but it is easy to take the limit in infinite volume limit of this stuff. And you will see that this equation defines Gaussian functionals of the form that I already described, with some specific values of n of k, which are called occupation numbers. So basically you can consider this this case, this quadratic functional quadratic Hamiltonian, you can consider it very easily in the formalism of L functionals. And you can go further. So really what I describing on this slide is the description. What can you do in this situation for L functionals? So really, first of all, you can. So what you should consider, what you are interested in. The first thing that you are interested in are evolution operators. And the first thing that you can do, you can write down the expression of the evolution operator in terms of functional integrals. If I will have time, I will talk about this a little bit. From functional integrals, or in any other way, you can consider, you can derive what is called a perturbation theory for evolution operator. You can consider the following thing. You can consider the Hamiltonian, which is a quadratic Hamiltonian, plus something. And something called perturbation. And you can put a number depending on time in front of this perturbation. If you have time here dependence of these coefficients of time, if it is slow, it is if you can neglect the derivative of g with respect to t, then we are calling about adiabatic perturbation. So you can consider adiabatic scattering matrix either in usual formalism or in the formalism of L functionals. You can consider limits of this adiabatic scattering matrix when the parameter of this describing this adiabatic property tends to 0. And so that's from adiabatic scattering matrix, in usual case, you can get a usual scattering matrix. In the formalism of L functionals, you can get something similar. And but this will be not scattering matrix, but inclusive scattering matrix. This which is closely related with inclusive cross-sections. So basically, in the case of adiabatic, in the case of L functionals, you can repeat more or less everything that you can do in quantum mechanics and quantum field theory. In particular, what is interesting, you can define a notion of green function in the formalism of L functionals, but this will be a kind of generalized green function. It contains usual green functions, and it contains also green functions that appear in Keldysh formalism of non-equilibrium statistical physics. So I wrote this definition of generalized green function. It corresponds to two stationary states, one in the space L and another in dual space. This again, it is defined in terms of chronological product in usual green functions. You take times decreasing, and here you do the same stuff. But the operators see that appear in the definition of green function. they can be either in the form A or in the form A tilde. Remember that every operator in the algebra gave me two operators in the space of linear functionals. So I have this doubling of fields as physicists are saying. So, and really, you can prove quite easily that you will get this green function that I have written in the case of when you are working an algebraic approach. You can take alpha from the, you can take one of the states from the algebra, which is, remember that L is a dual space of the algebra. So that elements of the algebra, they define linear functionals on L. So, and you can write down these equations for this formula for green function, generalized green function, in the following way. You have omega m alpha n, where m and n are chronological and anti-chronological products. Remember that in the definition of my green function in the formalism of L functionals, I have had two types of operators. I could multiply from the left or from the right, and in one case I take conjugate operator. But the left multiplication and right multiplication, they give me basically chronological and anti-chronological product. Because going from the left to the right, I change the order. And so basically, what I'm saying, that the formalism of L functionals gives me more general case of green functions that for alpha equal to 1 coincides with Keldysh green functions. But all the stuff is, I have no time to explain all the stuff. But what I would like to do right now, not right now, but after the break. So?
When it is convenient to make a break.
Yeah, this is the break time. So the only thing that I would like to say is that the next thing that I would like to explain is how the stuff works in quantum electrodynamics. And right now it is the break time, but you can ask questions either at this moment or during the break. So what I would like to talk about is infrared problem in quantum electrodynamics. This is really a very good example of applications of this formalism of L functionals. Why? Because
Hilbert, so much, just a question. So I know the description of this infrared problem in terms of what is called coherent states. And do I understand correctly that what you are going to describe is something similar to these coherent states, right?
That's correct. This is similar, but the case because really the very formalism of L-functionals is related to coherent states. This basically you can't really translate, I believe, one language to another language with one real problem, that really coherent states that you should consider in quantum electrodynamics, they lie in different Hilbert spaces. And this is a problem. People, I am not saying that people cannot solve this problem. In some sense, this problem is solved. But I think that the consideration right now, in terms of that I will present right now, in terms of L-functionals, probably is the simplest one. But what happens? Something about physics of quantum electrodynamics. Quantum dynamics, in this theory, you have electrons and photons. However, electrons are not really particles in standard sense. They are what is called infraparticles, because electrons do not correspond to poles in green functions. But physics, this is mathematically, but physically, simply electrons get dressed by photons. And so this is this electrons, which is dressed by photons, is described by a state which doesn't lie in Fock space. There are divergences here. So the second thing that when you consider scattering in quantum electrodynamics, then it is necessary to consider inclusive what is called inclusive cross-sections. Because, for example, if you have two colliding electrons and they give you also two electrons at the end, they definitely give in the process of collision, you have radiation, you have some photons which are soft, this means that they have very small energy. However, they are always there. So, and therefore, this formalism of L-functionals that is closely related to inclusive scattering matrix is really very natural in this situation. What I will do right now, I will consider a very simple problem. When this is not a complete quantum electrodynamics, you have in this problem, you have some current denoted by J, which is considered as a numerical function. So you have the photons that are quantized, and you look what happens. So what basically what do you have here? You can imagine that you have an electron moving say in some potential field, and you assume that photons do not influence the movement of the electron. But this is physical interpretation. But one can say that, another thing that one can say that the first paper where this understanding of infrared problem of quantum electrodynamics, this was a very old paper by Bloch and Norsig, where the same conditions were accepted. So I have this Hamiltonian. But at this, of course you can try to solve it in usual way. And you will find that Fock space is not sufficient for your calculations. So that's in the paper by Kulish and Fadeev, it was found that they found the right way of describing these dressed electrons. In the standard language of Hilbert spaces. What I will do is I will show that in this formalism of L functionals, you have no problems at all. Look what happens. You have this Hamiltonian, and using this Hamiltonian, you can write down the equation describing the evolution of corresponding L functional. In fact, I did explain how to do this. This is standard constructions, standard calculation that. So you have this Hamiltonian, and you go to L functionals, and you get the equation. So what is written? This equation is this equation can be written standard evolution equation, and you can easily calculate this equation, this dynamics that corresponds to the Hamiltonian that was written there. And now you don't have question about Hilbert spaces or so on. You should solve this equation. That is an easy problem.
In physical language, this L functional, what you call, is just wave function, right?
It is not, you don't have wave functions here. What do you have is with L functional, if you maybe the better. The
usual language, it's wave functional, that's Schrödinger equation. that you have written, right?
Yeah, but this is not this is not written for wave functions. You have, first of all, you went to density matrices from wave functions, and after that you,
Yes, it's sort of generalization of Schrödinger equation, density matrix, yes.
So,
I mean, usual Schrödinger equation is dp psi over dt is equal Hamiltonian acting on psi. And for density matrix, you have commutator.
You have commutator, yeah. And after that, you from density matrices, you go to L functionals. This is the formula that I explained. The L-functional maybe for you it will be more understandable. L-functional, so if you have density matrix, you have what is called Wigner function.
Okay, understand.
So that's, that's L-functionals. They more or less correspond to this Wigner function.
So they are defined on the phase space. It's not. They depend on the phase space, not on the.
Yeah. But L functionals, but more or less up to some irrelevant stuff. They can be identified with Wigner functions. And the only difference is when you are working with Wigner functions, you work with basically in Hilbert space. But this is the main contribution of L functionals, is that you can forget about Hilbert space. So you can consider the Wigner functions as basic material. And this is the explanation of the theory of L functionals that probably is appropriate for you, but not for other people in this audience. So basically, what is written here there are equations for Wigner functions. If this is more understandable for you. Yeah, there are equations that can be solved more or less immediately. Look what happens. This is the standard way to solve the equation of such a kind, is to go what is called interaction picture. This means that you have some kind of change of variables where you multiplied this evolution by evolution of free Hamiltonian. But anyway, after some trivial change of variables, you will get the equations of motion that has the following property. You have here the equation is linear with respect to operator C. That appears in operator C and C star or C plus is denoted here. And this linear equation can be solved. To solve this more or less standard stuff. So basically, what do you get here? The solution of any equations which are linear with respect to C and C star is up to some numerical factor that is not written here. is an exponent of is e to the some linear exponent. And after that you differentiate. You can write this equation, the solution in this form. You differentiate it. And you see that you will have this exponent satisfies the equations of the form that you want. And you see that you have really the explicit formula for the solution of your equation. So the solution is written here. This is, you solve the equations for operator of evolution, and you can rewrite the stuff as a formula that gives you the solution for L functional, starting with at moment t, starting with L functional at some moment t0. You solve this equation. And after that, when you solve this equation, you can really calculate sorry for interrupting myself. So here, what I said here is that the solution of this equation that is written here, it is consistent with the solution that was suggested by Kulish and Fadeev for this dressed electron, for they realized that to have a good formulas for scattering of electrons, you should first of all dress them. And so this formula that I obtained in this very simple way, it is an agreement with Kulish-Fadeev picture. So you can rewrite this formula that I have written. It will be look very similar to semi-classical formula. Basically, you can introduce notation, which here is A of K and C. This potential, which corresponds to J that we fixed. And so that's what do you have is an expression of L functional in terms of this potential A. After that, So what can you do? You can calculate inclusive cross-section. So what is inclusive cross-section? Inclusive cross-section, basically to calculate inclusive cross-section, you have particles with operators A, K, A star K, S, creation and annihilation operators, you should simply calculate, say that A star K, AK is the number of particles. You should calculate this number of particles. There's one more difficulty that you should consider. Out operators here. But anyway, this is, I don't want to go into detail here. What happens here is that you can really calculate this formula for inclusive cross-section.
You mean total inclusive cross-section?
So?
Total inclusive cross-section. You are interested in the...
No, not a total. No, that inclusive cross-section. So let me go to the formula. What this is this inclusive cross-section. What do you have here? This is the basic formula.
Yes, but there is no parameter. I don't see a parameter which characterizes the width of the wave packet. So a coherent state can be defined with a parameter which just tells you how many energies are in the portal, more or less.
So what?
I mean, it's total cross-section, which...
So what is the total? This is not total. It is a cross-section that depends on K1, Kn. You have
it depends on the initial momentum, right, of particles.
So you have so everything is embedded in all my initial conditions are embedded in J.
Well, the K are initial momentum, right?
Initial momentum, yeah. So you have...
In principle, you could also consider the quantity where there is initial momentum, but it's rest electron, right? And you can dress it in different waves with some parameter which characterizes the width of the corresponding wave packet. And was there just a question that here there is no such parameter in the quantity which you read, right?
So right. So basically, what do you have here? Here, this what is hidden in this formula is the fact that you have J, this current, embedded in the Hamiltonian, and this current, when you consider scattering of particles, then you first of all you should calculate this current, and this is so this A depends on the choice of the current. So definitely here you have cross-section of particles with momenta K1, Kn, inclusive cross-section. I do not look at other and so that's, but it depends also at initial momenta that are embedded in the current. So that's really only what did I explain? I explained a very simple picture where you have J as the current as a numerical function. Of course, this is not a complete quantum electrodynamics. But I do not claim that at this moment, I know everything about complete picture in quantum electrodynamics. However, I would like to say the following. What do you have in quantum electrodynamics? You have action functional that is action function of electron, action function of photon, and something describing the interaction. Interaction is precisely integral of J multiplied by A. J is here the current, and which for electrons will be simply psi bar gamma m psi, and A is vector potential. What I would like to say that you can write down all this stuff in terms of L functionals. You can, for example, in Coulomb gauge. And after that, you can integrate out photons. Then you can write down the functional integral. And you can, in this functional integral, you can integrate this. Really, you have a doubling of photon fields. But you go to L functionals as usual in Keldysh formalism, and you can integrate over photon fields, and you will get something that, as far as I understand, doesn't give you inclusive scattering matrix, that doesn't have any divergences. And this is more or less what people expect in quantum electrodynamics. But what in quantum dynamics, quantum electrodynamics, what happens is really cancellation of divergences. What happens in quantum electrodynamics? That you have divergences going from soft photons and divergences going from virtual photons. And they cancel each other. I believe what happens in the formalism L functionals. There is no cancellation. There are no infrared divergences at all. This is my expectation. However, at this moment, I cannot say that this is true. And now I think that, so let me say a couple of words about the slides that I didn't cover. So really, what is necessary to do in all this business with L functionals is to give a description of this picture in terms of terms of functional integrals. And yes, you can do this. You can do. You can represent the Pareto evolution in terms of functional integrals. You can represent a diabatic scattering matrix in terms of functional integrals. You can represent green functions in terms of functional integrals. You can get a representation of scattering, inclusive scattering matrix in terms of generalized green function on shell. So that's, I think that what did I really wanted to say is that all the stuff can be done in terms of functional integrals. It can be done without functional integrals also. But what is written here, that you can write down functional integrals from symbols of operators. This was done by Berezin and Hilbert space. And what is done with my paper with Frolov is generalization of this picture to Banach space in the way that it can be applied to L functionals. So, and by the way, this work about quantum electrodynamics, the simple example, also was done together with Frolov. So I do not think that I would like to use remaining minutes to go through slides about functional integrals. So at this moment I would like to ask if there are any questions. About the stuff. So then the only thing that I would like to say that the third lecture, this lecture was independent of the first lecture, and the third lecture will be independent of this one. In the third lecture, I will, in the third and fourth lectures, I will explain what does it mean generalization of what is called Hague-Ruel theory and Lemon-Simanchik-Zimmerman theory to L functionals. So I will start with some explanation of the situation in classical theory. I will talk about scattering of solitons, and I will discuss the notion of particle and quasi-particle as elementary with excitation of ground state and general translation invariant stationary states, and I will discuss the notion of how this Hilbert theory can be generalized to prove the existence of inclusive scattering matrix. The existence of scattering matrix cannot be proven. This was proven in non-relativistic quantum theory. But the existence of inclusive scattering matrix can be proven. And this is important because scattering matrix does exist only in series with where you have what is called particle interpretation, and inclusive scattering matrix does exist in situation when doesn't exist the scattering matrix with usual sense doesn't exist. Okay. Let me add this point. And at this point.
Thank you very much. So let's thank the speaker.